So folks, in this video I'm asking you to compute the solutions to this 4x4 system of equations. So you can count, we've got 1, 2, 3, 4 equations with 4 unknown variables that we want to solve for. This is a 4x4 system. And if I'm asking you to solve this via Cramer's rule, what we're going to do is we're going to construct these 4 different 4x4 determinants. This is very similar to what we did in these earlier problems, such as this one here, where when we want to figure out the coordinate solutions to the system of equations, we found the determinant of the coefficient matrix. This was our coefficient matrix. And then we also had to find 3 different determinants of something that looked like our coefficient matrix, but for the first variable we replaced the first column with the b vector. For our second variable we replaced the second column with our b vector. And for the third variable we replaced the third column of the original coefficient matrix with that b variable. So we're doing the same thing now, it just extends upwards to this 4x4 system. One thing that's a little bit challenging about this then is that means that if we want to solve this system, this 4x4 system, we're going to have to compute 4 separate determinants. That's not the end of the world. You can see, for example, here is the coefficient matrix A that I got from getting each of the coefficients of the entries on the left-hand side of this equation. And this matrix is populated with a lot of zeros, which we know makes computations like determinants quite a bit easier. But there's a couple other things that I want to just make sure that you're aware of as you're working through this that will probably be a time saver then for you. So besides this fact that this has a lot of zeros in it, and besides what we learned about determinants, which says we can expand by minors along any row or column, so we can be judicious in that, picking a row or a column that has a lot of zeros, I also want to point out our properties of determinants. And this was in our section 2.2 handout, where we went through the properties of determinants. And I have a hyperlinked video of me going through that if you don't have those notes. And I talk about these various properties. The video is about 10 minutes long and it's worth looking through. But there's one key property that I really want to point out because I think it's very useful here. This property says that if 2 rows or columns are identical, then the determinant of that matrix, or maybe it's a submatrix, will be 0. So for example, here I have this matrix A, and it's this 2x2 matrix, but look at the first row, or the first column and the second column, they're identical. So without any computation, I conclude that that determinant will be 0. Likewise, here I've got a 3x3 matrix, and notice that this row and this row are identical, so without any computation, I can conclude that that 3x3 determinant will be 0. So that's going to be useful as you're working through Cramer's rule here. If you notice, so I want to show you here, I've started to find the determinant of the 4x4 coefficient matrix A. That's what I'm in the process of computing here. And if you notice that, then what you can do, or if you look at this, say this 3x3 right here, when I started to set up this 3x3, I noticed that my second row and my third row were identical, so that told me that entire determinant would come out to be 0, and I avoided doing a lengthier computation there. So even though I had this messy 4x4 determinant that I'm supposed to calculate, I ended up only having to do one 3x3 determinant, and that one, if I was careful, in this case I think I opted to, well I didn't say it on here, I think I opted to expand along this row here, so I've got a couple of zeros, and so I only had to compute a 2x2 determinant and then just not get lost in the signs of everything. So folks, I'll show this to you. You're welcome to, I guess, pause the video and work through, but I would encourage you to try this on your own. In computing my A1 matrix, I replaced that determinant for Cramer's rule. I replaced the first column with the B coordinate vector. That was that 7, 0, 0, 0. So this looks like the original coefficient matrix, but the first column has been replaced by that B vector. And again, I noticed that I had a row here of two identical rows, and so I was able to conclude that that determinant was 0 without doing any of the computation, which was an incredible time saver. So not all of these result in big time savings, but I think that coupled together you should be able to come up with the solution without too much work. I guess you're welcome to pause the video, but you really ought to try these on your own. Finally, here is the eventual solution that you should get, 0, 7, 7, negative 7 for this system of equations. I hope this helps, folks. If not, please let me know. I'd be happy to answer any questions, and I'll see you next time.